This is a video on how to write a program to solve a simple Kakuro puzzle. This is an example of an unsolved puzzle. And just to recap, Kakuro consists of a grid in which linear groups of empty cells must add up to a specific number. These are examples of groups and their sums. Here is an example of a solution for this puzzle. All the cells must contain unique numbers from 1 to 9. They cannot repeat in the same group. To solve this puzzle, we will follow an algorithm, a procedure, and we will use Dialog APL for this. The procedure we will follow will be outlined here. It was determined in a previous video that you can find here. There are better and faster procedures, but this one will be used to see how to use a programming tool to investigate the problem. Here is the procedure. First of all, we must find the groups and their sums. The puzzle is divided into groups of cells, each with a sum to attain. We must find those groups and their sums from the argument. The argument of this program here will be a matrix of numbers. We will get into that a little bit later. Here we have assigned a number to each one of the cells. The number is an integer ranging from 0 to the number of cells minus 1. Here we have 4 rows, 4 columns. We have 16 cells. They are numbered from 0 to 15. Here is the first group. Here is the second group. And here is the third group. This group here is made up of the cells 9, 10, and 11. This one is made of the cells 5 and 9. And this one is made up of the cells 11 and 15. The next step is to find the cells to solve and their possible values. A 5, a 9, a 10, 11, and 15. Next, we find the groups each cell belongs to and the possible values for each one. Cell number 5 belongs to group number 1. Cell number 9 belongs to groups 0 and 1. Cell number 10 belongs to group 0. Cell 11 belongs to group 0 and 2. And cell number 15 belongs to group number 2. The 3 cells of group 0 must add up to 20. There are only 4 sets of numbers that can do that. And here they are. The 2 cells of group number 1 must add up to 4. The only way to do that is with the numbers 1 and 3. And the 2 cells of group number 2 must add up to 10, and there are only 4 sets of pairs that can do that. Now, cell number 5 belongs to group number 1. The possibilities are only 1 and 3. It cannot be anything else. Cell number 9 belongs to 2 groups. There is only one possible choice here. 3 is the number that appears in both sets. Cell number 10 belongs to group 0. There are 7 possibilities. Cell 11 belongs to group 0 and 2. There are 6 possibilities. And cell 15 belongs to group number 2, and there are 8 possibilities. We have now found what the possibilities are for each one of the cells. If any of them has no possibility, then the puzzle cannot be solved. We are now ready to group over cells with unique possibilities. The first thing we'll do is find the groups it belongs to. Cell number 9, which has only the number 3 as possibility, belongs to groups 0 and 1. Next, we check if that cell is in the list of numbers that have already been used in these groups. At the moment, none of them have been used. If it had been used, then we would know there's no possibility for the cell and none for the puzzle either. We now add 3 to the groups of cells done for groups 0 and 1. So we mark the cell of this puzzle with this number. Cell number 9 will contain number 3. The next thing to do is to reduce the sum of those groups by the number in the cell. For example here, since cell number 9 is member of group 0 and 1, group 0 has 20 as sum, and we've already used number 3. So the sum now will be reduced to 17. Likewise, group number 1, which was 4, will have to be reduced to 1. Now, group 0 is down to 2 cells, which must add up to 17, and group number 1 is down to 1 cell, which must add up to 1. So now we recompute the group's possibilities, and we can see that group number 0 can now contain only the numbers 8 and 9, and that group number 1 can only contain the number 1. Recomputing the cell's possibilities, we find out that cell number 5 can only contain the number 1. Cell number 9 has already been done. Cell number 10 can only contain the numbers 8 and 9, just like 11. And then cell number 15 hasn't changed. We now have another cell with a solution. Cell number 5 can only contain the number 1. We iterate one more time and end up in this configuration. There are no more possibilities. These three cells don't have a unique solution. Sometimes this procedure will find a unique solution, sometimes, like in this case, it won't. We will see later how to solve this, but for now, let's go over that with APL code. So here is our first attempt. The argument is a matrix of numbers. All the puzzle information is there. On line 6, the first thing we do is to prepare the result in case there is no solution. This is a simple string explaining that there is no solution. On line 8, we find all the group's sums and all the cells in them. Cells are given a number to identify them. It could be anything, it's not really important. But here, they are given the offset in the puzzle. If a puzzle has 4 rows and 4 columns, there are 16 cells and they are given the numbers 0 to 15. Find groups, sum, and indices takes care of that. I'm not going to show it here. This is outside the scope of this problem, but if you are interested, have a look at this video here. On line 9, we find all the cells to solve and each group they belong to. Each cell can belong to one or two groups. Cells of is a small function that will take care of that. It will return all the cells involved in the puzzle as well as the indices of the groups each cell belongs to. The way it works is like this. It receives all the group's cells as argument. Every cell involved in the puzzle will be there, sometimes twice if it is a member of two groups. Line number 2 will find the unique ones and sort them out, just like this. Let's imagine that we have a number of cells here. If we look at all the cells together, this is what we have. If we take the unique ones, these are the ones, and sorting them returns that. This is what line number 2 does. Line number 3 will find where each cell is in each group, and for each one, find the index of each group, like this. Now we have the cells. We verify where each cell is in each group. We split that on the first axis, so we get every row separately. And if we look at the indices of the group cells, there's only 3, 0, 1, and 2. And if we put them next to each other, this is what we get. We can see that the Boolean vector will compress the indices on the right. And if we do that, we get the result. It tells us where each cell is member of which groups. On line 10, we find all the numbers of cells in each group. On line 11, we initialize the cell's solution to 0 to mean it's not been solved yet. On line 14, we find the set of possibilities for each group. On line 16, we find the set of possibilities for each cell. And on 17, how many such possibilities there are for each cell. On line 18, if we find that there is at least one cell without any possibilities, we know the puzzle is unsolvable, and we bail out, we exit, we branch to 0. The result will be the string already set on line number 6. On line 19, we find all the cells that can contain only one number, and on 20, we initialize the sets of numbers used so far for each group to nothing. On line 23, this is where we reduce the sets of possibilities for each group. If we find that there is at least one cell with a unique solution, then, on line 24, we find them all, there could be more than one, and their position in the list of cells to solve. On line 25, we know the values of those cells for a later result. And on line 26, for each cell with a unique solution, on 27, we find the groups it belongs to. On 28, we correct the sum for these groups by subtracting the number in that cell. On line 29, we add the number to the sets of numbers used so far for those groups. On line 30, we reduce the number of cells in those groups by 1. On 32, we find the new sets of possible values for those groups, and on 33, we remove any set that includes any of the numbers used so far. After we've done all those cells with a single number in them, we recompute the possibilities for each cell on line 35, and on 36, we find any new cell with a single possible value, and start again on line 23 if there are any such cells. When cells with a single solutions are no longer found, we have exhausted the possibilities, and the variable C values contains the values in the cells that had a unique solution. If any is left, we can't tell which value to use, and the puzzle remains partially unsolved. There are ways to further solve some puzzles, but this is not the aim of this procedure. It only leads us to this point, which is pretty far. Let's see it work. Okay, so we have this variable here called P43 that returns a, we can't see very well. Let's turn boxing on and try again. Okay, that's better. We can see that these cells here contain the sums of the groups below or next to them. So we have to solve these 5 cells, and these others here are not doing anything. The program needs a matrix of numbers to work, so we have to turn this information into numbers. So I have this little from matrix of strings that takes a matrix of strings and turns it into numbers. You can see here that the empty cells where we need to solve the problem have been turned into a 0, and that the sums have been turned into complex numbers. The other ones that are unused have been turned into a -1. This is another one of those utilities that I'm not going to show you here. If you are interested, have a look at this link here. So we'll take this, let's put that into a variable called 40 and 43 for numbers 43, and let's try to solve using the program solve one with n43. And it works. It has found a solution. Let's have a look at the way it works. Let's call it again. So we have the program now. We're on line 1. Let's go straight to line number 6. We set the result to no solution, just like we had before. Now we call the program find groups, sums, and indices, which turns gsum. It gives us the 3 sums that we had, 13, 4, and 7. See there? And this gives us all the cells that are in each group, 4, 5, 10, 11, 5, 8, and 11 on the third group. So that worked. Let's find the index of all the cells that were used. Yeah, there are 5 of them. They're all there. And these are the groups that they belong to. Looks good. Let's find the number of cells in each one of the groups of cells. 2, 2, and 3. So far, so good. We initialize the values to all zeros. We don't know what their values is yet. And then we find a combination for each one of the groups. The first one can only be 4, 9, 5, 8, 6, 7. The second one, 3. The last one, 1, 2, 4. That's okay. I'm not going to explain how this program works here. If you want to know how it works, there's a little video that you can see here that explains all the gory details. For now, all you need to know is that we get the possibilities for each one of the groups there. On the next line, we try to find all the possibilities for each one of the cells. What we want to do is find the possibilities for each cell. For cells with only one group, it's easy. We simply take the unique numbers in their group. For example here, cells 0, 2, and 3 only contain one group. All we need to do is extract the unique values in each of their groups. For example, for cell 0, which belongs to group 0, we do. For cell 2, which belongs to group 1, we do. For cells with 2 groups, like cell number 1, which belongs to groups 0 and 2, we need to also do the intersection of both groups. In this case, we have, these are the 2 groups, and we can do the same as for one group, the union of the ravel of each group, then the intersection. We could write multiple statements, one for the cells with one group and another one for the cells with 2 groups. But we can also make those with one group act as if they had 2 groups by replicating their only group with 2 reshape. Like this, we can use only one statement for all of them. So now we have a matrix of indices. Some of them repeat. These are all the possibilities. Again, some repeat. This is the union of the ravel of each one of the groups, and this is their intersection. So we execute that, We now have our 5 results, one per cell. And then we take the number of results for each one of the cells, are 6, 1, 3. So we can see there are two that are unique, second and the last one. And here, if there had been any one with 0 possibilities, we would have exited, but this was okay. So we find the single ones, the second and the fifth one, and then we initialize the cells that are done to nothing. So initially there won't be anything in there. So while there is at least one cell with a single possibility, and this is true in this case, then we find all the numbers to remove, which is number 4 and number 1, and the cell is the second one and the last one, cell number 1 and cell number 4. So we set the values to the proper numbers, 4 and 1. And then for each one of the cells to remove, we find the first one, which is going to be 1. We find its groups, which are 0 and 2. And for each one of those groups, we had the sum here, which was 13 and 7, 0 and 2. We're going to remove the cell. So we now have 9 and 3. We subtracted 4 from each one. And in the done groups, we add 4 in those two groups. We subtract the number of cells in those groups, so 2 and 3 to 1 and 2. And we find the new possibilities, and we remove all the ones that we've done so far. So if we look at GPOS at the moment, the group possibilities, these are the new possibilities. So now we go for the second one, which is now cell which contains the number 1, and this is the last cell. We find its groups, which are 1 and 2, and in the groups in those cells is 4 and 3. So we are going to remove cell which was 1, so now we're going to have 3 and 2. And then on the groups done, we now catenate the number 1. We subtract the number of cells. We find the cells that are needed. We find the group possibilities. And we're finished with these guys. So we recompute the cell possibilities. And then we find that there's 3 new cells, unique. So we keep going with this new batch. I won't do this in detail. I'll process each quickly. Once we reach here, we check for cell possibilities and find there's no more. And all have been processed as C value shows no zeros in it. We now put our findings in the result and we return it. So that's how it works. We have another one here. So if I do, it also finds the solution. I have another one, P44. Let's try to do this. Oh, this one didn't find a complete solution. So there are 3 cells where we cannot tell for sure which number goes in there. It's an incomplete puzzle. This group of 3 cells originally added up to 20, and now there are 2 cells left that must add to 17. So it's either an 8 or a 9. We don't know. And in this group here, 2 cells that must add to 10, and it's either a 9 and a 2 or an 8 and a 3. So there are 2 possibilities here. So how can we fix that? Before we do that, we need to address a problem with this procedure. If we run a few tests, we soon realize that this puzzle here is problematic. If we try to solve it, we can see that it returns incorrect result. Obviously, we can't put ones all over the place. So let's trace through this problem here. If we follow the code, we see that the groups are okay. We have 1, 5, and 2, 4 for a sum of 6, 1, 2 for a sum of 3, and 1, 3 for sums of 4. And that the only intersection for the cells possibilities is 1 for all of them. And at this point there is nothing wrong. It is quite possible for many cells to have the same value. So if we keep going down here, we process the first cell, put the number 1 in its groups of numbers done. So far so good. Then we process the next cell, but we do not check if this new number in the cell, number 1, has been used. This info is in G done. And here we can see that it has been used and that it is not allowed. Therefore, this cell, which we thought had a single possibility, does in fact have none. And the puzzle is unsolvable. So we need to change the code here. Let's try this new version here. We do the same thing. We keep going. We get the same thing, the same possibilities for the groups, the same possibilities for the cells. But this time when we get here, we process the first cell. We go through, and when we get to the second cell, we check that it is not member of the group. If it is member of these groups, then we exit and we return the matrix of 0 that we had set in case this is unsolvable. So this program solves the problem that we have here. Now let's go back to the problem of several possibilities. When the program solve2 receives a matrix of numbers, all the zeros denote places to solve, and we go on, initializing the sets of cells done for each group to nothing, and proceeding to add to these sets as we solve each cell with a unique possibility. There is nothing that prevents us from accepting an already partially solved puzzle as input, and initializing the sets of cells done for each group to what we see in the argument and go on from there. We will need to modify this program here, but that's easily done. For example, if the puzzle contains a group of 3 cells adding up to say 20, we would normally set the group sum to 20, its cells to solve to 3, its set of done cells to nothing, the possible sets for that groups to this, and the possible numbers for the 3 cells to numbers from 3 to 9. But if we see that the first cell in that group contains, let's say, 4, then we know that the real sum to attain is 16, 20 minus 4, that there are 2 cells to solve, that the set of cells done is 4, that the possible sets for that group is 7 and 9, which is the same as the numbers that are possible for the 2 cells. And we can do this for all the groups in the puzzle. Now, obviously, if we feed such a program an unsolvable puzzle, it won't be able to solve it by definition. We will need to modify it not to terminate immediately if there are unsolved cells. What we can do is this. Let's take an example. P44 here. Let's trace through this. Here is the numeric translation of this puzzle. We keep on going. We determine the sums as usual, the cells as usual, and the groups done. They're all empty. This is the beginning of this puzzle. And then we trace through this, and we end up here. So when there are no more cells with unique solutions, like here, we check that there are no cells to solve with 0 solution. If there are any cells with 0 solution, then we know that the puzzle itself has no solution. In that case, we stop and return 0 solutions, not a bunch of zeros like we had before, but an empty array of solved puzzle. And what we've done right up here is that we've set the result to an empty array of puzzles already, not a bunch of zeros as in the other version. So if there are no solutions, normally we would end up here, but it is not the case here. So otherwise, if all the cells to solve have been determined, there's no loose ends, then we have a solution and we return an array of one solution, one puzzle solved. Again, here, this is not the case. We have some zeros in there. We have some unsolved cells. So we go on to here. And otherwise, we have several possibilities. And we're going to create a new puzzle with the cells that we found. This is the one here. Now, the new puzzle will contain, we can see the 1 and the 3 that have been determined. Then we pick one of the cells with multiple possibilities. Here, I pick the cell with the fewest possibilities. And I create as many new puzzles as there are possibilities. And for each one I put one of the possible numbers for that cell, like this. So here, in this cell we put an 8, and in this cell we put a 9. So we're going to try both possibilities. I then ask the program itself to solve all these puzzles. Each may return 0 or more solutions, and I gather the results into an array of solutions. So we're going to trace into this one here. Remember, there are 2 puzzles to solve, and this is the first one. We can see that we only have 2 groups to solve, this one and this one. So the sums are 9 and 10. 9 for the first one, there's only one solution, and 10 is for the other one. And the groups done, we have 3 and 8 in the first group. That is correct. So we keep going. And once we reach here, we found both cells and we have a solution. Here's the first result. We exit and then we trace into the second puzzle, which has a 3 and a 9 now. So the same thing. Here are the sums. This time it's an 8 and a 10. And the groups done this time is 3 and 9. And when we reach here, both cells have been done. We found a new result. We exit. We come back here. Now the result, we have two results that have been found. Both results have been gathered into an array of two results, two puzzles solved. We return and we have both results. So we seem to have created a program that solves Kakuro puzzles. Let's try it on a couple of other puzzles. Here's P3. It's a 4x5. The solve2 program cannot solve it, but the solve program has no trouble at all. In fact, it returns 19 solutions, so this seems to be working pretty good. Here's another one. That's a pretty large one. Solve2 is again unable to solve this one, but program solve takes a long time to find a solution, but it does find one eventually. In conclusion, we can see that APL was helpful in finding a solution to this problem. We found a solution that works. We now know it can be solved fairly easily, albeit not quickly. In another video, I will show how to solve Kakuro puzzles quickly, using the full power of the language. Until then, have fun.